Today we're going to talk about carboxylic acid derivatives. Carboxylic acid derivatives take a wide variety of shapes and characteristics. Shown here is a list of such derivatives, and how they're related to carboxylic acids and why they're called derivatives of carboxylic acids is instead of having an OH group attached to the carbonyl like a carboxylic acid would, we have some other potential leaving group. So we could have a halide, usually chloride. This would be called the acid chloride. We could have an anhydride. So in this case, we have a halogen attached to the carbonyl. In the case of the anhydride, we have a carboxylate group attached to the carbonyl. The ester has an OR group. The amide has a nitrogen group. And a nitrile looks a little different from all the others, but it too is a carboxylic acid derivative, and it has 3 bonds to a nitrogen. What most of these have in common, as I said, is having a leaving group attached here, and it's some group that has a lone pair of electrons. That's how we can identify something as a carboxylic acid derivative. And we describe it as a heteroatom, something that's not carbon or hydrogen. So a halogen, oxygen, nitrogen, so on. If we want to learn how to prepare these carboxylic acid derivatives, we really need to have a good understanding of the differences between the various leaving groups. And so one question we can ask is, how do they compare in terms of electrophilicity? So in exploring the features of the leaving group, let's ask which carbonyl is the better electrophile. Let's compare the ester versus the amide. Which of these is a better electrophile? To be a better electrophile means that you have more of a partial positive, right? You are less electron rich, would make you a good electrophile. And we can look at a few things: inductive effects, resonance effects. So for the inductive effects, remember that oxygen is more electronegative than nitrogen. Okay, so that means this oxygen is pulling electron density away from that carbonyl. What effect does that have on the carbonyl? Well, and actually we could state that because it's more electronegative, that means oxygen is better at withdrawing electron density inductively, meaning through the bond. Oxygen is doing a better job pulling this electron density away than nitrogen is. Okay, so as a result, the ester is more partial positive than the amide. So just based on these inductive effects, we expect that the ester is the better electrophile. However, that's not the only influence that these leaving groups are having on the carbonyl. Besides the inductive effects, the through bond effects, we also have some resonance effects. And that's because each of these leaving groups, remember, has a lone pair, at least one lone pair of electrons. And anytime you have an allylic lone pair, we can have resonance. So the other thing that this oxygen is doing is it's adding its electron density into the carbonyl. The oxygen can do that, and the nitrogen can do that. So let's take a look at those resonance forms and see how effective that resonance donation is. Okay, there's the resonance form for the ester, and here's the resonance form for the amide. We'll now have a double bond here, positive charge on that nitrogen, and our carbonyl oxygen is now a single bond with an O-. Okay, and what we want to ask is which of these atoms, the nitrogen or the oxygen, which of them is better at doing this resonance, at donating its electron density that way, and which of these resonance form is a bigger contributor to the overall picture of the ester or the amide. When I look at these two, I see that I have an O+ versus an N+. Now, are each of those elements equally good at handling a positive charge? They're not, because we know oxygen is more electronegative than nitrogen. So the nitrogen better handles a positive charge. That means this resonance form is a larger contributor to the overall picture of the amide. So what we can say is, let's restate the fact that nitrogen is less electronegative than oxygen. So N+ is better than O+. In other words, nitrogen better handles the positive charge because it is more electropositive than oxygen. Okay, that means that nitrogen is better at donating at donating its electron density. Because that's what's happening in this resonance. The lone pair from nitrogen is going into the carbonyl. That's a donation. That's adding electron density. So that means the amide carbonyl, what is the effect on the amide carbonyl? It's more electron rich. Because the nitrogen is very good at sharing its electron density, the result is this carbonyl is more electron rich than the ester. If we come over and we look at the ester situation, we could say that oxygen is more electronegative, and we could say it doesn't want to share its electron density. It doesn't want to share its lone pair. It's more electronegative. It's more likely to hold on to those, and it's less likely to share them because that would put a positive charge on the oxygen. Therefore, the ester carbonyl is less electron rich. It has less of that electron donation, and therefore it's not as electron rich as the amide. So looking at these two arguments, what would you conclude about the electrophilicity? Which is the better electrophile, the ester or the amide? The ester is the better electrophile. Both of these point to the same conclusion, is that the ester is the better electrophile. Turns out that that was the same conclusion we drew by the inductive effects. In this case, both the inductive effects and the resonance effects point to the same conclusion. Now, if we ever find that they point in different directions, which one do you think is going to win? I think the resonance effects are going to win because those are usually more important in guiding the reactivity. But let's see. Let's do another comparison. Let's compare now an ester versus an acid chloride. How about an oxygen compared to a chlorine? What effect is that having on the reactivity of the carbonyl? Well, again, we could think about inductive effects. Both the oxygen and the chlorine pull electron density away from the carbon. They're both more electronegative than carbon. Oxygen even more so because, remember, oxygen is the second most electronegative atom in the periodic table. So that's definitely a strong dipole. But let's jump right into the resonance effects because that's where the most significant difference is going to lie. So once again, it's always going to be the same picture. We can take one of the lone pairs from our leaving group and share it with the carbonyl to draw a contributing resonance form. It'll always put a positive charge on the leaving group and a negative charge on the carbonyl oxygen. And chlorine can do that too. Take one of its lone pairs and add it into the carbonyl. And then just like we did before, let's look at these two resonance forms and see which of them, see if we can predict which of them is having a bigger influence, having a bigger impact on the overall structure, which is the bigger contributor. Now we're looking at an O plus versus a Cl plus, and this is a little more looking at apples and oranges because we're not looking at a direct periodic trend here. The oxygen and chlorine are not in the same row, they're not in the same column, okay? But there's something interesting about this chlorine. How often have you seen a chlorine involved in a double bond with carbon? That's a very rare structure and structural element, and the reason for that is because the chlorine is so much bigger than the carbon that when it tries to share that pi bond with its large p orbital, it can't do so effectively. So what we could say is that chlorine is too big for a good pi bond. We could describe it as having poor orbital overlap. We're trying to overlap a 2p orbital with a, 3p orbital with a 2p orbital, and there's not good exchange there. So this pi bond is a very weak bond. That means it's not a very significant contributor to the overall resonance hybrid. So we could also describe that as saying that chlorine doesn't want to share or is not capable of sharing its electrons, its lone pairs. Okay, and so oxygen now compared to chlorine, oxygen is actually better at donating its electron density because it's matched better with the carbon size. The oxygen is better at donating its electron density. So what does that do to the ester carbonyl compared to the acid chloride carbonyl? The ester carbonyl is now the one that is more electron rich because it has more of this electron donation. The ester carbonyl is more electron rich. And so who is the better electrophile in this case? The ester versus the acid chloride? Is being more electron rich a good thing for an electrophile? Just the opposite. That means the ester is a poor electrophile compared to the acid chloride. So both of these combine to tell us that the acid chloride is the better electrophile. Acid chloride is a better electrophile than an ester. Let's take a look at one more comparison. How about a carboxylic acid compared to an anhydride? Anhydride is kind of an interesting structure because we have these two carbonyls. And now we're comparing an oxygen leaving group versus an oxygen leaving group. So that we really have no difference inductively in terms of electronegativity. Let's again jump to the resonance to see what those resonance forms look like. The carboxylic acid resonance form looks just like the ester resonance form, except we have a hydrogen here instead of an R group. And then for the anhydride, that oxygen can do the same thing. Okay, what's the difference going to be then? We have an O plus versus an O plus. What's the difference? Well, are there any additional resonance forms that we can have? Sure, because we have two carbonyls here, we know that's going to be significant somehow. Instead of having this lone pair come over to the left to share with the carbonyl on the left, it can also move over to the right and share with the carbonyl on the right. So let's look at that resonance form. That we would get back to by shifting this pi bond over on the other side. So this carbonyl is intact, but now this carbonyl has the O minus. And so that's going to be the difference between the two. We have some extra resonance with the anhydride. Okay, the big question though is how does that affect electrophilicity? Remember, to be a better electrophile, you want to be more partial positive. We don't have a carbonyl that's a partial positive. So let's put it this way. This carboxylic acid has an oxygen that donates its electron density full time to the carbonyl. There's nothing else for this oxygen to be doing in terms of resonance than to share with this carbonyl. So we'll say the acid oxygen donates to only one carbonyl. If we kind of look at it this way, perhaps you'll see the difference. What is this oxygen doing? It's spending its time delocalizing its lone pair to both carbonyls. The anhydride oxygen lone pair is shared between two oxygens. I'm sorry, between two carbonyls and onto two oxygens. Okay, so what does that do to being more electron rich, more electron deficient? Looks to me like this carboxylic acid carbonyl is going to be more electron rich because this has the full-time donation, where this carbonyl is not going to be as electron rich because sometimes some fraction of this lone pair is going to be shared with the carbonyl, but only half because the other half is going to be shared with the other carbonyl. So this does not have effectively as much electron donation. So the ester carbonyl, I'm sorry, we're looking at carboxylic acid here. The carboxylic acid carbonyl is more electron rich. So who is the better electrophile? The anhydride is the better electrophile. And don't think that it has something to do because there's twice as many carbonyls. Remember, just one carbonyl we're looking at as the electrophile. The other carbonyl is part of the leaving group. So we're just comparing this one carbonyl to the carbonyl in the carboxylic acid, and what we're seeing is we're not getting as much electron donation because the presence of the other carbonyl draws some of that electron density away from the first carbonyl. So overall, we can continue doing these comparisons in pairs, but overall we're going to be able to develop an entire scheme of an order of electrophilicity. And it turns out that this order also parallels the order of leaving group ability. So at the far end here, we have the acid chloride. Let's take a look at the leaving group for each of these acid derivatives. A leaving group for an acid chloride would be Cl-, would be chloride. That's a pretty good leaving group. We've seen that before in all sorts of substitution, elimination reactions. A halide would be a very good leaving group. The leaving group here is carboxylate. This is a carboxylate anion. The leaving group here, we're putting both of these kind of together. They're not hugely different in terms of their reactivity. So either an alkoxide or hydroxide as your leaving group. Both are similar in their reactivity, very similar. Here we would have an NH2- leaving group. And what if we had a carboxylate itself as our electrophile, and we did a substitution, in other words, a nucleophile added into the carbonyl and kicked out this leaving group? What would the leaving group look like? I think it would be an O2-. That doesn't look like a very good leaving group. Okay, so hopefully you can see that but as you compare these leaving groups, we're getting poorer and poorer in terms of leaving group ability. So let's take a look at the acid chloride and see some conclusions we can draw here. Okay, the acid chloride at the far end here is the extreme. This has the best leaving group. What does it take to be a good leaving group? What defines a good leaving group? It's something that is very, very stable, is a weak base. And so those are some things we'll look for. It's stable, it's a weak base. That's what determines leaving group ability. And like I said, a halide is a leaving group in all sorts of situations. So we recognize it as a good leaving group. Okay? It also has least amount of resonance donation by that leaving group. So remember, the chlorine was so large that it was not very effective at sharing its electron density with the carbonyl, so it did not have very much electron resonance donation. That makes it the most reactive. Doesn't have a lot of resonance, so that makes it less stable. It makes it more reactive. It also makes it the most electron deficient carbonyl. Right? All carbonyls are good electrophiles. When you put a chlorine on there, that chlorine pulls electron density away inductively and doesn't add much back in by resonance. So it's a very, very reactive, very electron deficient carbonyl. And so this is by far the best electrophile. This is a great electrophile. And acid chloride is super reactive. We're going to see it react with any nucleophile you want to put in there. It's going to be happy to react with. Okay, that's slightly better than the anhydride. The anhydride is also a very good electrophile. It's got a good leaving group. What makes this a good leaving group? Well, it has resonance stabilization, right? That negative charge is delocalized over both oxygens. So that's a pretty good leaving group too. Okay, but that is a better leaving group than that we would have on the ester, the carboxylic acid, because now alkoxide, hydroxide, these are strong bases. These are not particularly good leaving groups. And because this has more electron donation by the oxygen than the anhydride would, the carbonyl is also more electron rich and therefore less electrophilic. Remember, the nitrogen is real good at donating its electron density. So this is very electron rich. Nitrogen is an N- is much less stable than an O-, so our leaving group is continuing to get worse and worse. And then we get to this final end where now our species is negatively charged. That's an extremely poor electrophile if you're negatively charged. Remember, we want to be electron deficient to be a good electrophile. So let's come all the way down to this last example, the carboxylate, and let's describe some things we see on this extreme. Okay, this has the worst, meaning least stable, leaving group. Least stable, strongest base. Clearly O2- would not be very happy leaving on its own. It also has the most resonance, and O- would be very effective at sharing its electron density by resonance. In fact, the second resonance form would be just as big a contributor as the first one because it would be equivalent. So that's the best resonance you can have. So that makes it the least reactive carbonyl, in terms of electrophilicity, because it's the richest, it's the most electron-rich carbonyl, and that makes it the worst electrophile. It's the worst electrophile. So really you should be able to compare any of these carboxylic acid derivatives like we just did for a few pairs. You should be able to compare them, and really you should know this order. You should know this order of reactivity. You should understand it. So this is not a random list that you should memorize. It's something that should make sense to you, because what we're going to be doing is we're going to be doing these comparisons again and again. Because the way you make a carboxylic acid derivative typically is you start with another carboxylic acid derivative and you just swap one group for another. Okay, we call that a carboxylic acid derivative interconversion, and that's the way we're going to be synthesizing and preparing these various carboxylic acid derivatives. For example, if I were to take an acid chloride and react it with methoxide, I could look at the product where the chlorine and the methoxide have exchanged. We've done a substitution where now I have an ester and the chloride leaving group. Okay, now this mechanism is going to start with the acid chloride acting as my nucleophile and the methoxide, the acid chloride acting as my electrophile, the methoxide acting as my nucleophile, and it's going to add into the carbonyl. That's going to give me the following intermediate. Looks like a CTI. It's a charged tetrahedral intermediate. And when this collapses, this O- kicks back down, we have two possible leaving groups to kick out. And every time a CTI collapses, it's going to collapse to lose the better leaving group. So it's critical that we know which is the better leaving group. Who's the better leaving group here, methoxide or chloride? Chloride is the better leaving group. So this is going to come down, kick off the chloride, and go back here. Okay, and if we think about this reverse reaction happening where the ester is my electrophile and the chloride is my nucleophile, this chloride can attack back into the carbonyl to go back to CTI. But is it ever going to go back in this direction once the chloride adds in? Is the O- going to kick out the methoxide? No way. This reverse reaction this is a one-way street here. We're never going to be kicking out the poor leaving group when we do our CTI. So that's how we can decide the equilibrium. Direction of the equilibrium is going to lie, as usual, in the direction of the better leaving group leaving. So we can look at the better leaving group. This is the better leaving group. Okay, the methoxide is the better nucleophile. And of these two electrophiles, comparing the ester to the acid chloride, which one's the better electrophile? Remember, the acid chloride was the best electrophile. So it's better than all the others. So it's the better electrophile, and the ester is the poor electrophile. So all these things we can look at in a variety of ways, looking at the more reactive carbonyl, looking at the better leaving group. Whichever way we look at it, we're going to get the same answer. We should get the same answer. In this case, it's the forward reaction that's going to be favored, where we displace the better leaving group with the better nucleophile. And we go from a more reactive carbonyl to a less reactive carbonyl. Okay, which means since the acid chloride was the most reactive derivative with the best leaving group, that means we can start with the acid chloride and go anywhere. We can replace that with any other group that we want. So the question then that I have for you is, so how do we make the acid chloride? How is it possible that we ever put a chlorine in there if that's such a good leaving group? And that is an excellent question. Let's see how do we do that. So we'll call this the preparation of acid halides, and the chloride in particular. And what we're going to do is we're going to take we're going to start with the carboxylic acid, and we're going to react it with either thionyl chloride or phosphorus trichloride. These reagents should look familiar. These are the same reagents we use to take an alcohol and convert it to an alkyl chloride. And so what these do is they first react with the hydroxyl group here. So just a quick hint at what's going on. I'm not going to go through the complete mechanism. But so, for example, if you had thionyl chloride, this oxygen can add into the sulfonyl and kick out the chloride. What you do is you make a great leaving group. You make a really great leaving group, one that's so great that even a chloride can displace it and kick it out. So you can, in fact, make the acid chloride this way using either SOCl2 or PCl3. If you ever need to make an acid chloride, you have to start with a carboxylic acid starting material. Now, how would I make an anhydride? There's a couple of different ways we can make an anhydride. One possibility is by the dehydration of a carboxylic acid, and this would be a way to make symmetrical anhydrides. So in other words, an anhydride where the two carboxyl groups on each side are identical. One way to get there is to start with the carboxylic acid, the parent carboxylic acid. So here we have a 1, 2, 3 carbon on each side of the anhydride, so we start with the 1, 2, 3 carbon propanoic acid. And if we heat this mixture, we can lose water. So that's why we call it an anhydride. It is the carboxylic acid having had water removed, okay? And we need, this must be removed in order for this reaction to occur, because if you don't take this away, then what will happen is the anhydride, very reactive anhydride, will react with water, will get an additional elimination, it will get a substitution to go right back. So in order to push the equilibrium forward and move it forward, we need to remove this product to get the reaction going. And what's happening is we have two equivalents of our acids. So one is acting as the nucleophile, one is acting as the electrophile. So just kind of the key, I'm not going to do a complete mechanism for this, but here's the bond that's forming as the OH group is adding in, and then eventually you're going to be eliminating this leaving group and replacing that leaving group. So that's one possible way to synthesize an anhydride. Let's see an example of that. This is succinic acid. It's an example of a dicarboxylic acid, and if you heat this up, and in the presence, especially in the presence of a drying agent, this is acetic anhydride, and that's kind of an inexpensive anhydride you can use that loves to react with water. So you can put that in there, and it will act as a drying agent when it sees water. It will react with water to make acetic acid. It's going to make two equivalents of acetic acid. So this is just an example of a drying agent that can help get rid of the water and push the equilibrium forward. So if we go to predict the product here, again, one of the carbonyls is going to be the electrophile. The other carbonyl, it's the leaving group part, that's going to be the nucleophile. So there's the bond that we're forming. And we're going to do an addition elimination. So we're losing this OH, and we're going to lose this H as well. So that's how you can see that we're losing a molecule of water. And what size ring would this form? It's a diacid, so when these two ends react together, it's going to form a ring. What size ring would that form? 1, 2, 3, 4, 5. It's going to form a 5-membered ring with an oxygen in there. Looks something like this. And so this molecule is known as succinic anhydride because it is the anhydride made from succinic acid. That's the way we name anhydrides, is we just take the parent carboxylic acid and replace the word acid with anhydride. Now, if we wanted to make a mixed anhydride has two different groups on either side of the oxygen. We couldn't do that by a dehydration because we'd have to throw both different acids in there, and we would have no way of knowing who's going to react with whom. Okay, so instead what we're going to do is we're going to start with an acid chloride, and that's going to be our electrophile. We're going to add in a carboxylate nucleophile, and we have a sodium carboxylate. So anytime you see sodium, that means you have a sodium plus and O minus. So we can drop out that sodium spectator ion so I can see my nucleophile. I can see my acid chloride electrophile. Remember, really great electrophile. So let's see what the mechanism is going to look like to do this substitution reaction, get our product. So we have our carboxylate. It's going to attack the carbonyl, break the pi bond. So we'll have an O- up here. And what was the nucleophile we added? It was an oxygen with a carbonyl, and then a CH2 and a CH3. So there's our addition. Remember, overall, our reactions are going to be an addition and then an elimination. This elimination is the collapse of the CTI. This is the reaction the carboxylic acid derivatives undergo. Addition of a nucleophile, elimination of a leaving group. So now when I look at my CTI, my charged tetrahedral intermediate, and I decide which leaving group is going to kicked out, which one wins? Because we have two possibilities. Remember, a leaving group is anything with our lone pairs, so we have two possibilities. And while this is a good leaving group, the chloride is better. This is our better leaving group. So it kicks down and kicks off, and we go to our anhydride. It's possible that this reverse reaction can happen, but the favored reaction is right here, kicking off our better leaving group. So this is another reaction where we know we're going to push this reaction in the forward direction simply because we're displacing a better leaving group than the one we're putting in there. That's why it's so important to recall that overall order of reactivity and leaving group ability so that you know which substitutions are allowed and which ones are not. Okay, how do we get an ester? An ester has an OR group attached to a carbonyl. Okay, there's many ways to make esters. And one possibility is to start with a better leaving group attached to a carbonyl and then introduce the OR group. So what better leaving groups are there? Well, we could look at our two most reactive acid derivatives, the acid chloride and the anhydride. The acid chloride, great leaving group. The anhydride, great leaving group. And so in fact, in preparation of esters and amides and others, we'll find that very often anhydrides and acid chlorides are used interchangeably. They're both very, very good leaving groups. So let's see what will happen here. We're going to, there's our leaving group. Here's our nucleophile, the alcohol. Now we know we're going to have to lose this proton at some point. So because we're losing an H and a Cl, that's why we need a base in here to do that deprotonation. So we're going to get that salt. Pyridine is a nice base that's used often in a case like this. And so what does our product look like? We will have our phenyl with an oxygen, and now attached to that oxygen will be the carbonyl. We did addition, elimination. We did an acyl substitution, addition, elimination. And whether I used acetyl chloride or acetic anhydride, I get the exact same product, don't I? I still add the carbonyl with a methyl group. I added an acyl group in both of these cases, or an acetyl group. Okay, and for that reason, this is described as an acylation reaction. You could say that you just acylated this alcohol with an acid chloride or with an anhydride. So this is one very good way to prepare an ester. Okay, another option is to start with a carboxylic acid and react with an alcohol. This is known as the Fischer esterification, and the substitution reactions in the reaction occurs in the presence of an acid. And what we're doing is we're swapping the OH group for an OR group. We use ethanol to add in, and ultimately we kick out water. Now, here's a good question for this reaction, though. Which direction of the equilibrium do you think is going to be favored? Who is the better leaving group in this reaction? Because remember, the reverse reaction can happen too. The reverse reaction is where water adds into the carbonyl and kicks out the OR group. We saw that in the hydrolysis of ester reaction. Okay, so we know this reverse reaction is possible. So how do we know which one is favored? Well, in fact, the leaving group, the ROH and the H2O have about the same leaving group ability. So there is nothing naturally driving this equilibrium forward or backwards based on the stability of the products. The stability of the starting materials and the stability of products are all great. So we're going to have to do something to push it. We need to drive off. We need to remove a product to push the equilibrium forward. Okay, sometimes we can do something to react with the water or remove the water. One thing we could do maybe is distill. We can distill the ester off. This very often has a lower boiling point than our carboxylic acid and our alcohol, because these have OH groups. These are very, very polar starting materials. This is going to be less polar as the ester, so sometimes the ester can be distilled off as it's formed. Okay, but we need something, some strategy to make the Fischer esterification work. Or maybe you could have a huge excess. Right? If you have a huge excess of the alcohol, then that would be something that also can push it forward. Okay, it needs to have some kind of acid catalyst. So sometimes we just write HA, but it could be something like sulfuric acid, tosic acid, HCl. Okay, any sort of acid in there is good. We wouldn't want to use H3O plus as our acid, though, because water is one of the products we're trying to get rid of. So you wouldn't want to be adding water into your reaction mixture. Okay, so what is the mechanism here? Again, it's addition elimination for an acyl substitution. Turns out that it is the exact reverse of the hydrolysis mechanism we've already studied. Hydrolysis was when we took an ester in the presence of an acid and reacted it with water. So the same number of steps that we took us to the hydrolysis, carboxylic acid, and alcohol, the exact same steps, the exact same intermediates are what we're going to be seeing today and going to the in the other direction, doing the Fischer esterification. Okay, so let's do the mechanism. Where do you think we should start? I think we have acid catalyzed conditions, acidic conditions, so I'm guessing the first step should be protonate something. Now there's a whole bunch of oxygens we can protonate. We can protonate here, we can protonate here, we can protonate here. Okay, and those will all happen reversibly. We'll protonate everywhere. But where's the place that will protonate that will actually move us in the forward direction? It's the carbonyl oxygen that when we protonate there, we're going to get an intermediate that has some enhanced reactivity, and therefore will start moving us toward the substitution product, okay? Because when you protonate a carbonyl, you make a great electrophile. You turn that partial positive carbon that was already there into an even more partial positive carbon, even more electron deficient, so it's a great electrophile. So we'll start by protonating the carbonyl. Now we have to find a nucleophile. Of course, our nucleophile is our alcohol, maybe even our solvent in this case. And so it's going to attack the carbon and break the pi bond as usual. Now this oxygen still has the ethyl group, it still has the hydrogen, so we have to put both of those on there. And what else does it have? It still has one lone pair and looks like a positive charge, doesn't it? Oxygen with 3 bonds and a lone pair. 1, 2, 3, 4, 5. Oxygen has 5, it wants 6. So we have an O+. Okay, so we're getting there. We put in the ethoxy group. Let's deprotonate. Let's get rid of that positive charge. We can use A-. We started with HA, so we could just use A- to come back and grab that proton because it is catalytic in acid. So every protonation step is going to be coupled with a deprotonation step. And we're starting to move in the right direction. We know we have to add in this ethoxy group, and we just did that. How did we do it? Protonate, attack, deprotonate. Again and again, we see that pattern for acid-catalyzed mechanisms. Protonate, attack, deprotonate. Okay, so now where do we go? How do we move forward? What else do we need to accomplish? Remember, it's a substitution reaction. So we added in the ethoxy. What do we need to take out? We need to remove this OH group and substitute that OH group. Well, now we see either of these can be used. There's no distinguishing them anymore. But how are we going to make it eventually leave? We're in acidic conditions, so we need to protonate it to make it a good leaving group. So let's pick the one on the side here and protonate to make it a good leaving group. And how is it going to leave? How is that leaving group going to leave? Looks like I have a CTI, so with 2 arrows, I can collapse that CTI. That would be a great way to lose the leaving group. Not just leaving group leave on its own, but having this oxygen lone pair push it out. Okay, what's great about doing my mechanism that way is look at where it brings us when we do that. When you lose a leaving group with assistance from that lone pair, it brings us right to an intermediate that looks this close to our product, right? All we need is to get rid of that last proton. So it's a very good habit to get into, is using those 2 arrows. Notice we just kicked off our water here. If you like to keep track of your leaving group, you can see that you just generated the other product that we're forming in this reaction. And then for our last product, we can just bring back the A- and deprotonate, and we're done. So we just made an ester. We did an acyl substitution reaction, addition elimination. Remember, it is acid catalyzed. So what kind of charges do we expect for this mechanism? All our charges, they're neutral or they're positively charged. We can't lose hydroxide as a leaving group. We can't use ethoxide as a nucleophile, and so on. Okay, let's make sure we're using just strong acids to protonate and have no O- charges as we go through. It's called the Fischer esterification, the combination of a carboxylic acid and an alcohol. Let's see if we can predict a product. If I were to take this molecule that has a carboxylic acid and an alcohol in the same structure and treat it with some acid. Remember, tosic acid is just like sulfuric acid. It's just organic soluble. And we throw that in with some heat. What reaction can happen here? Well, let's look for a nucleophile. Let's look for an electrophile. I see my carbonyl. That's going to be an electrophile. This is going to be my leaving group that gets displaced. And where's my nucleophile? This oxygen is going to be my nucleophile. So the key step, the key bond that I'm forming without doing a complete mechanism, I can see the bond that I'm forming, and we would be creating a ring in this situation. Now, what size ring would we form? We want to make sure it's allowable before we do a cyclization. So let's count. Oxygen is 1, 2, 3, 4, 5, 6 atoms. That looks like a perfect size ring to me. So we have a 6 atom ring. One of those atoms is oxygen. So there's 1, 2, 3, 4, 5, 6. 6 was the carbonyl. And it was the carbonyl with the OH, but remember, one oxygen adds in, kicks out the other oxygen. We end up doing a substitution. We lose this proton during the mechanism. We lose this OH during the mechanism. So water is our second product here, must be lost in this Fischer esterification example. Now, another way to prepare esters is a reaction called a transesterification mechanism. Transesterification is when we go from one ester to another ester. And here I have an ethyl ester. If I took an ethyl ester and dissolved it in methanol, then I would get the methyl ester out and create some ethanol as a leaving group. Now, this might be a strategy you want to employ because you one ester is commercially available, but you want to have a different ester, so you want to replace that OR group. But where this really comes into play is very often as an unwanted side reaction. Let's say I was using this ethyl ester and I just happen to use methanol as my solvent in my reaction without thinking of it. What's going to happen besides whatever reaction I wanted to have happen is some of this transesterification. So anytime you have a mismatch between the OR group of your ester and the OR group of your alcohol, we can get this swapping, we can get this substitution to take place. So if I didn't want this transesterification to take place, what would be a better solvent for me to use with this ester starting material? I would use ethanol as my solvent, and then this transesterification reaction wouldn't be a problem. It would still happen, ethanol would still add in, but it would be kicking out ethoxide, and it would be an invisible reaction. Okay, so we can't eliminate the substitution reaction. We could just put in a nucleophile that matches the leaving group that's already there. Okay, so once again, comparing our leaving groups, methanol, ethanol, you can't get more similar in terms of leaving group ability, so there's nothing that's naturally driving this forward or back. We need to use the Chatelier's principle and either having a huge excess of one, like having it as a solvent, or we drive off the other in some way. We have to do something to push the equilibrium in one direction or the other. Okay, the mechanism is exactly analogous to the Fischer esterification. We're going to protonate as our first step. I'll just abbreviate that as ethoxy. Let's go through this one more time because it's great practice. We'll protonate as our first step. That makes super electrophile here. We look around for a nucleophile. Now we can have our nucleophile attack. So remember, acid catalyzed, we do protonate, then attack, and then deprotonate. So here's our attack. And then we deprotonate. Now you might think, well, wait, didn't we just have a CTI? Couldn't that CTI collapse? Couldn't this CTI collapse? It could, but who is the best leaving group in this CTI? The leaving group is down here. It's the methanol. So if this CTI collapsed, where would it bring us? Right back to where we started. Okay, so yes, this is reversible. This is reversible. We can add in the methanol and kick it back out. Okay, but if we have something pushing the equilibrium forward by Le Chatelier's principle, we're going to keep moving forward instead. And now we would protonate the ethoxy group so that we could get that as our leaving group. Always keeping in mind where we're trying to go is how we can be guided in a mechanism. So I didn't want this CTI because it had methanol as my good leaving group. I want ethanol as my good leaving group. So what I did was I deprotonated down here and I reprotonated up here. Now I'm ready to do a collapse and kick out the leaving group I want to kick out. Here's my CTI and here's my 2-arrow collapse. So I just lost a molecule of ethanol and I recreated my carbonyl. And all I need to do is deprotonate, and I'm at my final ester. So this is called a trans-esterification. If you look closely at the mechanism on the previous slide, you'll see that this is completely analogous to a Fischer esterification, but instead of having a carboxylic acid starting material, an OH here, so that you lose water, you have an OR here, so that you lose an alcohol. Okay, finally, another way that you can make an ester is to, instead of doing a substitution at the carbonyl where you install an OR group, you start with an oxygen, like a carboxylate, and then you add an alkyl group to the oxygen. So it's just doing a disconnection. The ester syntheses we've seen up till now have been forming this new bond by doing a substitution reaction at the carbonyl. And now we're taking a look at the possibility, well, another way you can make an ester is if we form this bond. That could also give an ester product. Okay, so we could do that by an SN2 reaction. If this was our nucleophile and this was our electrophile, then we could have something like an SN2. If we had the carboxylate nucleophile and we reacted it with an unhindered electrophile like this primary alkyl halide electrophile, looks like a pretty good SN2 reaction. Carboxylate's a good nucleophile. We expect it to do an SN2. And I just made an ester. Okay, so obviously this can only happen if you have an unhindered leaving group. So this is only good for building esters that have primary, or maybe methyl groups here that are possibly secondary, because this is a pretty good nucleophile. E2 doesn't compete too well, but it does have to allow the SN2 mechanism to take place here. Another interesting reagent that you can use to make an ester this way is called diazomethane. If you take a carboxylic acid and react with diazomethane, I've shown the structure here of diazomethane. The first thing that happens is our carboxylic acid donates a proton to the diazomethane, which acts as a base. Diazomethane actually has a C-. So we can do a proton transfer here. And that does two things for us. It gives us a nucleophile now. Now we just made the carboxylate, which is a good nucleophile. And it gives us a carbon bearing, a neutral carbon bearing a great leaving group. What's the leaving group here if this were to get displaced? It would be nitrogen gas. So the product we get in this, just a backside attack SN2 mechanism here, carboxylate now attacks the methyl that was just formed and kicks off nitrogen gas. And we just formed a methyl ester. So diazomethane is a unique reagent that can only make a methyl ester because it is a one-carbon electrophilic reagent that delivers that one carbon as a methyl group. So that's an interesting reagent, and a nice way you can make a methyl ester in particular, taking advantage of an SN2 mechanism. Let's see if we can do an example of a transform reaction. If we started with this alcohol, how can we turn it into this ester? So here we see that we are forming this bond. That's one way we can kind of look at it both ways. We could disconnect here or here, but let's take a look at this disconnection. Okay, the oxygen was my nucleophile, and the carbonyl was my electrophile. So if I had this O minus, that would be a good nucleophile, and I had this carbonyl, that would be a good electrophile. But the question is, what is attached to this carbonyl so that after the oxygen adds into it, I don't lose the carbonyl, I still have it? How can that happen? What I need is a leaving group. Something like an acid chloride would be an ideal leaving group. If I had a good leaving group there, then this could do an additional elimination, and I would retain my carbonyl. So this looks like a straightforward acylation reaction. I just would use benzoyl chloride, an acid chloride, and some base, maybe like pyridine. And I would do additional elimination, and the pyridine would be there to react with the HCl byproduct. Okay, what if we wanted to make an amide? Now, remember that amide was the very last one of our carboxylic acid derivatives in terms of reactivity. It has the worst leaving group, so we could imagine that maybe we could start with any other leaving group there, and the nitrogen will always be good enough to kick it out and displace it. And that's mostly true. Let's see several examples. So first of all, we can start with our acid chloride or anhydride. Remember, those are the two best leaving groups, and that would be a great way to make an amide. So for example, if I started with this amine and I wanted to make this amide, I just added a 1, 2, 3 carbon carbonyl. So just like we did in the transform, if I used an acid chloride, I could do addition of the nitrogen, elimination of the chloride, or I could use the 3 carbon anhydride. So instead of a chlorine leaving group, I could have a carboxylate leaving group. Both of these would be great at doing the transformation, additional elimination. Okay, but remember, we always have a base that's thrown in here because we have to remove that proton, and here we'll lose a chloride, so we're forming HCl here. Or if we use the anhydride, we would form the carboxylic acid as a leaving group. So we need some kind of base in here, and like I said, sometimes we use pyridine as a base. That's very common. Okay, but because amines are bases, sometimes what we do is we just add 2 equivalents of the amine. One of them will get acylated, and the other one can act as the base for the acid that's formed. So sometimes if you see that there's an excess of the amine that's starting here, that's what it's being used for. Rather than use an amine and then throw in a second amine to act as a base or a pyridine, then we could just do 2 equivalents of the amine to act as the base as well. Okay, so one possible route to an amide, one of the best routes to forming an amide, is to start with the acid chloride or the anhydride and do a simple addition elimination with an amine nucleophile. Another synthesis that's unique to amides is to start with a nitrile, a CN triple bond, and do just a partial hydrolysis. So we saw that one way to make an amide is to start with a nitrile. And so one possible way to do this transformation, for example, is to first install a cyano group. We would use sodium cyanide to do an SN2 here with cyanide. So that's a good way to introduce a cyano group to a carbon chain. And now what we want to do is replace two of these CN bonds with CO bonds. That looks like hydrolysis. So H3O plus mild. We'll do just a partial hydrolysis. We'll start hydrolyzing the nitrile. But if we don't add heat, then we can get it to stop at the amide product. So this is another way that we can make an amide, thinking about in terms of a retrosynthesis, going back, doing a functional group interversion back to a nitrile instead. What would be another way that we can do this transformation? We see we have two carbons here, and we're adding this one carbon that ultimately would be an amide functional group. Let's think of another possibility. Well, let's go back and say, well, what's another way that we can make an amide? The first possibility we saw for making an amide was from an acid chloride. So what if I made this acid chloride instead? If I had this acid chloride, could I make the amide? Remember, this retrosynthesis is asking what starting materials do I need? Well, if I had this acid chloride, I could just mix it with ammonia and that would make the amide. So this would be a good possibility. Well, where do acid chlorides come from? Acid chlorides come from carboxylic acids. If I had this carboxylic acid, I could make the acid chloride and then go to the amide. Right? So now I'm looking at a synthesis where I'm going from a bromide to a carboxylic acid. We've already seen the synthesis of carboxylic acids. In fact, we've seen the path where we do this disconnection. Let's imagine breaking that carbon-carbon bond of the carboxylic acid and asking which of these carbons was my nucleophile, which one was my electrophile. I think the carbon with the carbonyl was my electrophile, which means the other one was a nucleophile. How do I make an ethyl group nucleophilic? The Grignard reagent is the way to do that. RMGX makes any random carbon group nucleophilic. And so what electrophile do you react the Grignard with to make this carboxylic acid product? We need an electrophile with a carbon and two oxygens. I think that's carbon dioxide. Yeah, we saw the reaction of a Grignard with CO2 as a way to make carboxylic acid. So this would be another path to doing this transformation. We could add in magnesium to make the Grignard reagent, where it just inserts itself into the carbon-bromine bond, and then we can do carbon dioxide followed by workup. To install the extra carbon as a carboxylic acid, and then we can convert that carboxylic acid to a acid chloride by using, so a special reagent is needed for this. We use SOCl2 or PCl5, a chlorinating agent like thionyl chloride. And then finally, how would I convert the acid chloride to the amide? Well, I could just use ammonia. I could use an excess of ammonia because I know I need some extra in there to react with the HCl. Okay, so this would be another path. Many times our synthesis problems or our transform problems will have lots of options, and we're seeing that there's a lot of ways to make these various carboxylic acid derivatives. Okay, now one thing I want to point out though is you might think, well, how about if I start with a carboxylic acid and I add in ammonia? Could I use that to make an amide? Well, at first glance it looks pretty good because when we compare our leaving groups, we say, well, yeah, the water is a better leaving group and the amines a better nucleophile, so I would think this would favor the products, okay? But the problem is this reaction does not work. It does not work directly, it doesn't work easily, okay? If you really cooked this and really add a lot of heat and did an industrial preparation, you could get this reaction to go. But in an ordinary laboratory setting, this reaction doesn't happen because a different reaction happens. And what is it about amines that are unique? What reactivity do they have besides being a nucleophile? And we just saw it on the previous slide. We saw that we use an excess of the amines, so it can also act as a base. Amines are very good bases. So the problem is we are adding a base to a carboxylic acid. What reaction happens? What reaction happens? We will have a proton transfer to make a carboxylate and ammonium. Okay, and what's the problem there? Well, the problem there is we now have a very, very poor electrophile. Excuse me, our carboxylic acid is now a carboxylate. Remember we said that was the worst electrophile we could have because it's negatively charged. And we've also lost our nucleophile because we have, this is not a nucleophile. And so like I said, if you had an excess amine and you really heated it up, you could get this substitution reaction take place, but under ordinary circumstances, there's no reaction that happens further here, so this would not be a way to make the amide. Okay, instead, the way you would do this, how could you convert the carboxylic acid to the amide? That's what we just saw. We saw first, you convert this into a good leaving group by using SOCl2. First, make the acid chloride. And now you can throw in that amine and make the amide. So it's just going to take an extra step. The way we make an amide is from an acid chloride rather than a carboxylic acid. Okay, so we've just explored all the various ways to make the different carboxylic acid derivatives, acid chloride, anhydride, ester, amide. Okay, now let's take a look at what kind of reactions they can undergo. And they all have carbonyls, so they are going to be electrophiles. So what we're really going to be looking at is the reactions of various nucleophiles. So for example, a hydride nucleophile. Let's review what hydride does with a carbonyl, such as an aldehyde or a ketone. If we had an aldehyde or a ketone, we react with either sodium borohydride or lithium aluminum hydride, any source of hydride, any of those sources of hydride. Remember, we put in quotes because it's really associated, it's bonded to the boron or the aluminum. But that's going to attack the carbonyl and break the pi bond, and then after workup, or thanks to the protic solvent we have here, we would get an alcohol. We describe this as a reduction reaction because we traded a CO bond for a CH bond. Okay, when we try to do the same reaction with an ester, with sodium borohydride with an ester, no reaction happens. There's no reaction. The sodium borohydride is not very reactive. We're going to be looking at sodium borohydride and lithium aluminum hydride separately. The sodium borohydride is not all that reactive. You can actually see that because it coexists okay with a protic solvent. So you can tell it's not all that reactive. And remember that the ester is less reactive than the ketone. It's a poorer electrophile compared to the ketone. Why is that? Why is this carbonyl less reactive? What effect is this oxygen having on that carbonyl? Electron donation by resonance. Okay, it adds an electron density that makes this carbonyl more electron rich, so it's going to be less willing to react with a nucleophile. Okay, so here's one difference we can see from an ester to a ketone would be a reaction with something like sodium borohydride. If we try lithium aluminum hydride, however, that's more reactive, and so it will, in fact, react with an ester. It will react with an acid. It will react with every carboxylic acid derivative you throw at it. It will react with nearly every functional group that you throw at it. Okay, LAH is a great reducing agent. So when you react it with an ester, you actually end up getting an alcohol product again, and it ends up adding 2 equivalents of the hydride are added. So let's see if we can do a mechanism for that. Lithium aluminum hydride is a source of H-, so we can draw H- in quotes. And I'm pretty sure the mechanism is going to start as usual. Nucleophile attacks the carbonyl. Let's see where that brings us. We now have a hydrogen added. We have an O- up here. Any guess on what's going to happen here? As usual with the carboxylic acid derivatives, because it has a leaving group on that carbonyl after nucleophile adds in, it's going to eliminate that leaving group. We have our CTI here, and that CTI is going to collapse to kick off a leaving group. So we get a substitution, addition, elimination, an acyl substitution. Okay, however, our reaction's not done yet because we just made an aldehyde. Does an aldehyde react with LAH? It does. In fact, the aldehyde is even more reactive than the ester that we started with. Remember, this is even better electrophile, so you can't stop here. This will not stop in these reaction conditions. They'll continue to react with the hydride that's present, and a second equivalent will be added. Okay, what now? Do we collapse? Do we continue? Do we get a third addition somehow? Is this a CTI? Is that a CTI, charged tetrahedral intermediate? It's not. It's tetrahedral, and it's got an O-, but what is it missing? It's missing a leaving group. There's no leaving group. Remember, a charged tetrahedral intermediate has two groups with lone pairs, at least two groups with lone pairs. So one group does the pushing out, and the other group with lone pairs is a good leaving group. So in other words, this is an irreversible reaction. Once you form a CH bond, you're done. You're never going to break that bond. H- is not a good leaving group. Methyl- is not a good leaving group. So you're done. So this just waits around for step 2. We should have the same step 2 H3O plus. So when you do a workup now, we're going to protonate this O-, and we get our alcohol product, which is what we predicted. We had 2 equivalents of hydride to the carbonyl. Addition, elimination, followed by a second addition. So let's summarize what we see with hydride. This is not true. This is true not only for esters, but it's true for any of these carboxylic acid derivatives. So even the carboxylic acid would do this, the acid chloride, the anhydride for sure, because they're even more reactive. All of these will have addition, elimination of our leaving group, and then a second addition of hydride to get an alcohol product. Okay, the only carboxylic acid derivatives that vary from this are the nitrogen-based ones, either the amide or the nitrile. Okay, these will also add 2 equivalents of hydride, but the product you get is not the alcohol, you get the amine. You keep the nitrogen that was in your starting material, doesn't leave. Remember how we talked about how poor a leaving group nitrogen is, doesn't like having a negative charge, and this is evidence of how poor that leaving group is. It doesn't get kicked out. So let's take a look at this mechanism, though, to see how we can get to an amine from something like an amide. And what happens in this mechanism first is a little unusual, and that's because our amide is slightly acidic, and we're reacting with hydride, which is a very strong base. And so the first thing that happens is we deprotonate the amide. Now, rather than just draw this as the anion, I'm going to add in this salt. Remember, this was LiAlH4. Okay, so the counterion we have here, we still have an aluminum with 3 hydrogens. That aluminum with 3 hydrogens and the lithium salt, this is all still going to be here kind of like a counterion. This is a Lewis acid. It's going to be adding to this lone pair. It's going to be stabilizing it. Okay, so it's not just a plain old nitrogen with a negative charge. It's forming a bond with this aluminum, and that's going to be stabilizing it. Okay, so even though it's negatively charged, this is just how reactive hydride is. It'll still get attacked by the nucleophile now, by another equivalent of the hydride. Okay, our nitrogen still has AlH3Li+. And now the oxygen has a negative charge, so let's draw its counterion, AlH3Li+. This is a very strange looking CTI, isn't it? It's actually got two charges, okay, but it is still a charged tetrahedral intermediate. Looks pretty unstable, but it will form. The question is, when it collapses, who's the better leaving group? Okay, they're both ugly. They're both looking pretty awful, but which one looks better? We have an oxygen that'll have negative charge or a nitrogen that has a negative charge. Because oxygen is more electronegative, it better handles the negative charge. This is the better leaving group. So what happens is the hydride adds in, and then the nitrogen, the existing nitrogen, kicks that oxygen out as a leaving group. And that's how the oxygen gets lost. Okay, so again, additional elimination like we saw before, but rather than have an aldehyde with a carbonyl, we have this imine with a CN double bond, but this is just like a carbonyl in terms of its reactivity. And because I still have hydride around, we would expect that second addition of hydride to occur, and it does. Okay, and again, this would be the salt here, but that's not going to be very relevant to us at this point because we're just going to be working up at this point. There's nothing else for it to do. Again, this is not a CTI. It has no leaving groups. The only thing it's going to do is wait around for workup so it can be protonated. So what product did we have? We end up adding 2 equivalents of hydride, but we keep that nitrogen leaving group. The first hydride adds in, and then the CTI collapses to kick out the oxygen, and then the second equivalent of hydride adds in as well. Okay, the mechanism for the amide, for the nitrile with the CN triple bond is a little more straightforward because you don't have that oxygen to get rid of. In that case, you just add hydride, and you add a second hydride with protonations in between. How about organometallic reagents, like a Grignard reagent? How would that react with a carboxylic acid derivative such as an ester? Well, again, let's review what we know about ketones and aldehydes in that carbonyl chemistry. If we used methyl magnesium bromide or methyl lithium, that's a source of methyl minus. Again, we put that in quotes because it's not ionic. It has that metal coordinated to it, but it's nice to draw it like this for our mechanism. Of course, great nucleophile. Carbonyl is an electrophile. So after our workup, we end up forming an alcohol, right? We get this new carbon-carbon bond. And with methyl magnesium bromide or methyl lithium, we would add this new methyl group. And we would get an alcohol product out. Okay, that's what we get for an aldehyde or a ketone. How does that differ when we use something like an ester? Okay, well now, again, we'll use methyl magnesium bromide. And it's going to add to the carbonyl and break the pi bond. I'm sorry, this is not an equilibrium. It's a one-way street because we're forming a new carbon-carbon bond. That makes an O minus. We have an O ethyl, and we just added a methyl group. So looks very much like it did in the hydride example. The nucleophile adds in. It forms a CTI that is going to collapse. To give a ketone. And can we stop at this point? We can't stop here. Remember, the ketone is even more reactive than the ester. So we'll assume that we have an excess available of the Grignard reagent so that we're going to be adding a second equivalent just like we did for the hydride. We're going to add 2 equivalents of the Grignards. And we're going to get an alcohol product. So essentially the same exact mechanism as the hydride, same looking product, except instead of adding an H, you're going to add some kind of R group, in this case a methyl group. Let's try an example. It's always a little more interesting when we look at cyclic examples. This is called a lactone. A cyclic ester is called a lactone. What would happen to this product if we were to react it with an excess of phenyllithium? Well, phenyllithium means we have phenyl minus. It's like we have phenyl minus. Let's see if we can predict this product without going through an entire detailed mechanism. Okay, I know that this is going to attack the carbon and break the pi bond. That'll give me an O- up here. What happens next? Then that CTI, that O- comes back down and kicks the leaving group out. So what we're going to end up doing is we're going to be breaking this carbon-oxygen bond here. Let's see if we can draw that product. Sometimes it's helpful just to redraw your ring and then literally erase the bond that's broken. There's the bond that's broken. And we're going to have a carbonyl because we did addition, elimination. We did a substitution. So we still have the carbonyl. We still have and we have introduced a phenyl. This we could draw as an O- because it got kicked out as a leaving group. And is that our final product? If we have an excess of the phenyllithium around, we expect the product to repeat. Okay, our phenyl- is going to come back in again. So in our final product, we'll have an alcohol with 2 new phenyl groups attached. And then our O- upon workup is going to give us an alcohol. Let's just check to make sure we still have, including the oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's good. We still have 6 atoms there. A lot of times when we're doing our line drawings and our, especially with cyclic systems, it's easy to gain a carbon or lose a carbon. Okay, so we see our pattern. 2 equivalents of our Grignard has been added, or lithium in this case, and we get an alcohol product. In this case, our leaving group is still attached, so our leaving group is still there. We see the alcohol leaving group in this case. Now there's a few special hydride reagents that I thought I'd share some examples with you. Rather than using just lithium aluminum hydride, which is super reactive and reduces the maximum amount in each case, we can look at some other derivatives of that. For example, if you, instead of just having 4 hydrides here, if you have 2 isobutyl groups attached to the aluminum, this is an isobutyl group, 1, 2, 3, 4 carbons. Kind of looks like an isopropyl. This would be an isopropyl, just those 3 carbons. Then it's got an extra CH2. That's called the isobutyl group. So this is called di-isobutyl aluminum hydride. So this is called dibal for short, or sometimes it's dibal H to show that it has a hydride attached to it. And because of the presence of those isobutyl groups, it changes the reactivity. It makes it more selective and less reactive. And it turns out it only adds 1 equivalent of hydride. So the H- equivalent is going to add. But when you form this intermediate, because it has the aluminum with the isobutyl groups on here, okay, turns out that this is stable. And there's no collapse here, so because there's no collapse, there is no opportunity for that second equivalent of the hydride to add in. So this just waits until workup, and we trade those 2 CO bonds from separate groups into CO bonds to the same oxygen, and we get our carbonyl back. So when you compare this product, you take an ester, and you can just do a partial reduction of that ester by doing a single additional elimination, a single substitution reaction, and not having a second addition added in. So you can go from an ester to an aldehyde with a special reagent like diisobutyl aluminum hydride. There's some other examples. You can put some terpetoxy groups on the aluminum to replace 3 of those hydrogens. So this one has that same sort of reactivity. Sodium cyanoborohydride has some special reactivity with the presence of the cyano group. So really there are dozens and dozens of reagents that you can use. We're really just looking at the tip of the iceberg, so we kind of look at the most commonly used reagents when we're first introducing a topic. And another interesting example with carboxylic acid derivatives is the use of an organocuprate. An organocuprate has the formula R2CuLi. We've seen organocuprates adding doing conjugate additions to alpha beta unsaturated carbonyls, kind of like a Michael addition, a 1,4 addition. So that's an interesting reactivity that cuprate has. It also has an interesting reactivity with an acid chloride. These have a different reactivity than a Grignard. It's less reactive. And when we use it to react with an acid chloride, like here we have diphenyl cuprate, the phenyl 2- is going to add in, and then it's going to collapse down, and we'll get an additional elimination. But then this product has no reaction, no further reaction with diphenyl cuprates. Cuprates don't react with ketones. So unlike the Grignard where we had additional elimination and then we added again, at Grignard you're always going to add 2 equivalents no matter what. It actually stops with the cuprate. So why does it react at all? Well, remember the acid chloride is more reactive. That's a very, very hot electrophile, very reactive, very electron deficient. The ketone is less reactive because it no longer has that leaving group on there pulling electron density away. So anytime you go to a product that's less reactive than your starting material, it might be a reaction that you can control and prohibit the further reaction going forward. Okay, so that wraps it up for a look at carboxylic acid derivatives. How do we prepare the various carboxylic acid derivatives, and what are some reactions that they can undergo? Thanks.